Good morning. Uh, I think for today's class, let me just finish a little bit from last time. This is nearly complete. This is about the reduction of order. Okay. So basically, reduction of order is one method to find a solution in higher differential equation if we know the other solution. So suppose that we have to find like two solutions. We know one solution. We need to know the other one. So we can try to make out this other solution as it's pretty similar to the substitution. We get using another variable to express the expression between the y2 and y1, and so far we are able to build up the new expressions, and then we can make out the first linear differential equation through this substitutions, okay? And then solved by the integrating factors, and then we get the new expression w as one of the solutions, and then we substitute back to the definition, and we get this solution. Okay? And from this expression, since we know the other solutions, which is the e to the x, so we are able to see that perhaps the other solution are e to the power negative x. Okay. But it doesn't really showing how generally this would work. So we need to have some general cases how we can use this method. Okay. So let's start with writing some general formula. Okay, so general case. So suppose we have differential equation in the form of a second order, so y double prime and assume that P and Q, they are continuous on some interval I. And then we let y1 as a known solution on the same interval. And y1 is not equal to 0 for every x in interval I. Okay, we are using the same process. Substitute some expression. So we are going to substitute y. Okay, we are going to substitute this. So then we have y prime. We are going to take product rule. Okay, product rule. And let me just write u and y1, okay, to simplify. And then second derivative, another product rule. Well, I will just write the results, okay? Okay, that will be the result. And then subs y prime, y double prime into differential equation. So we have y double prime plus p y prime plus q y. So we substitute u y1 double prime plus 2y1 u prime plus y1 u double prime plus p plus by prime is u y1 y prime plus u prime y1. So we substitute all the y prime and y double prime. Qy is u y1. Then we arrange all the structure based on, let's take u. This will be y1 double prime plus p y1 prime, right? And then plus q y1. Okay. So this will be this and this, right? So that's the first, and then the second one is u prime. U prime is 2y 2y1 oh, this is prime, sorry, this is prime, yeah. So 2y prime plus by1, and then plus y1 u prime, or u double prime y1, okay. Okay, this is the DE, right? This is the DE, and if you notice that this is the same form, so we can let this make it 0. So we are going to have u double prime, or y1 u double prime plus 2y1 prime plus by1 u prime equaling to 0. Okay. And then we change the u prime as w, so u double prime will be y prime. Okay. So this is what we call the reduction of order, is this part. Okay, so this is what we call the reduction of process, reduction of order. So actually using substitutions, and then from that substitutions we are reducing the order. So we can rewrite the new expression with w y1 w prime plus this become w. So let me just write
2y1 prime plus by1 w equals 0. Okay, let's divide all with y1. So we have w prime plus w over y1 multiply with this equal to 0. Now we can express this as expression for the first linear order. Maybe this will be better if I write y1 prime and then w over maybe this will be better, and plus bw and equal to 0. And I think if we let this expression, let's divide by w. So this will be 1 over y plus 2 plus, or let me write in the right side, minus b. Okay. So we can choose, if you want to make linear, we can choose linear, finding the integrating factor, or I believe this also can be separable because it's equal to 0. So we can separate this. So it means that we can have an integration for all parts here. We integrate with respect to x. So we can separate, or right here, or take integrating factor is e maybe just takes, let me just finish this first, okay, and then we can go for the other part. Okay. So after we take integrations, this will somehow, we get, this is ln and plus ln y1 squared, and this will be p dx, okay. And suppose that we have a constant on the right side, and then we have ln w y1 squared okay, and this will be p dx plus c. solve for the ln, we get the e with power of this, right? Also plus c, or let me write another constant c1. c1 is e to the power of c. And then the w is our u prime, so we can write u prime y1 squared equal c1 e. Okay. And then we solve for u prime, so we are going to have c1 e divided by y1 squared. Okay. To make it into u, we are going to integrate both sides. So then we have u equal, constant will be coming out, and this is the whole integration, c1, e with power of negative p dx over y1 squared dx, okay, this is dx, plus c2. Okay, now if c1 is 1 and c2 is 0, then y2, remember that y is ux y1x. Okay. Then y2 becomes equal y1x integration of the e p dx somehow we get the final like approach for the second solution directly like that. Okay. But actually the way we did like last time and with the direct approach, they are actually having this similar conclusion. But if you are using this method, you will get directly the answer. So remember, y1 and y2, according to the dependency, y1 and y2 need to be linearly independent. So if you have you still have some time to check, you can check using Wronskian. So it can be check using the Wronskian. So check the determinant. If it is not equal 0, it means it's linearly independent. It means that it's true that the y2 are the solution, the other solution that is linearly independent. And sometimes for some integrals, in all cases,
in our course. If somehow you find a function inside that is not integrable, it means maybe non-elementary function, then you are going to write with the integrations. Just skip the integral. Like in the integral, we call this integral defined functions. Okay, so it's still okay. And sometimes maybe in the problem set, you are actually given information about that. Like this will be integral defined function. So you don't need to like try to force out the integrations, but just skip the integration. It's okay if somehow you cannot integrate it. But usually, this P depends on the structure. Usually, the problem set will provide you some way to, like, because it's E and then you have something here that is usually will resulting in ln, and then you are going to cancel the ln, and then this one will cancel with this one, and you will get the result. But then you need to integral again. Integral. Oh, this one. But the limitation of this method is you need to know the other solution. You need to know the y1. Y1 you need to be given. So if y1 we know, then we can find the other solution, y2. Maybe I will give you like set example, maybe one example or two example. And I'm preparing additional videos related to some simulation or models to that can be applied using engineering of math, because I think because of the contents, so your midterm will be fully first order differential equations, okay? Including the introduction as well. And the second part of the courses is start from the higher order, and then later, I think maybe around after 2 or 3 weeks, we're going to a new section which we call the Laplace transformation. Okay. Laplace transformation is actually solving the same problem with the differential equations, but we are using some transformation that is supposed to be simplified all the methods that we have been given before. So that is the total courses, all the weeks. Okay, so we have a higher order and then Laplace later. Okay. And since I think I will just announce now. Since on the November, middle November, I think I will also not going to be in Taiwan, and also this first week December. So I think I will see if we are able to finish the higher order before the second week of November, then I think we still need at least one more makeup class. Okay? But I think that will be for November. Okay, November makeup class. But if for the last one, if we really haven't discussed much about Laplace, perhaps there will be only short section of Laplace that I think important for you. I would teach. Okay, but again, it depends on how our progress will be. Okay, because my goal, and actually
the final week should be in the from December 18 to 22, right? That will be the final week. But if somehow we need at least the final exam on, so by default should be on 21, not 21, 19 Tuesday class, right? But if not, then perhaps we need to have 26, okay? So between these two, 19 or 26, okay? And then we're done. But if you want like early, then we need to have like at least makeup class, 2 makeup class. Okay? So I will let you know if we have already passed 2 weeks in November. Okay, if we have passed 2 weeks in November, and I think maybe we need to have 2 makeup class, it means that we can go for final exam on 19. Okay? But if not, then final exam will be 26. Okay, so that's the, I think, some announcement just to let you know. Okay, I think we can set some example here. Okay. So example, let's say y1, if y1 is x squared, and it is a solution of x squared y double prime So actually, if you want to use like a normal substitutions and then reduce the order, and then solve by either by linear or separable, you still can do that, okay? And I think that will be more applicable because we already know how to solve by separable and linear. But if you're trying to use directly the formulation that previously we have derived, then we can directly use that, okay? So first, we have this equation, right? The first thing is we need to arrange the structure first. Okay? So let's divide by x squared. It becomes y double prime minus 3 over x y prime plus 4 over x squared y equals 0. Now this is, I think, the standard form, okay, the standard form. And then we can just write y2 is, this is y1, or let me write the total equation first. So y1, this is e, so this will be should be y double prime plus p of x y prime plus q of x y equals 0. So here p is this p and this q. Okay. So we can input the x squared, put here, and then integration. The y1 is x with power 4, become 4. And then e negative 3 over x dx, like that. And then integral again here. The integral for this one will be this will be minus, right? Minus, sorry, minus. So it will be plus, which equal to 3 ln x, or e ln x cube or x cube. Okay, so you see that we can cancel each other out. So this is, I think, a problem set to help us compute better. So x squared become x cubed divided by x with power 4, or this will be 1 over x dx. Or in our case, this is going to be that. Okay. So general solution, since we are not having any initial condition, so we need to write the general solution with a constant. So general solution c1 y1 plus c2 y2, or and then you can check that the x squared and x squared ln x, they are both linearly independent. Okay. Okay. Okay, now in the last 15 minutes, I would like to move to an introduction of another method. Okay, we can have this method as a review later on. Okay, we can have more examples later. And sometimes you are going to see that there are some equation that might be not easy to be taken into the standard form, in which you need to use substitutions, as previously described. Okay. I think as long as you can make this standard form, you can put this formulation. Okay, let's see what's next. Okay. So the next one is we call the homogeneous linear equation with constant coefficient. So it's a long name, but it's actually quite simple. So suppose that we have a differential equation. Let's say we have y prime plus ay. Let's say it's equal to 0. If a is constant, so if a is constant, then perhaps the solution, so we can write, become like that. So we are going to solve the y prime y, or if you just think any functions that when we derive, it has a similar structure with the previous equations.
Okay, and those function or those equation is the exponent, right? If we derive the exponent, the original equation will appear again. Like e with power of x, if you derive, it's still e power of x, right? But we have negative. So perhaps the most ideal answer or solution that we can offer is perhaps this is going to be
y is have a constant 1 like that, and then e with that.
So if we try to derive this, we can make out this structure here, right? At least. Right? So this equation e, the exponent, will be our key to solve the homogeneous linear equations. Because if we derive, we are going to see a lot in e. So e become really useful.
So if we have any higher order like an solution are either exponent or constructed out of exponential function. So it should have a component that is based on exponential. Okay. To give you some illustrations, let's start with the consider. Let's say we have a y double prime plus b y prime plus c y, and let it equal to 0. Okay, if we let the solution, okay, if we let y equal e to the, let's say mx, another value, another constant. If we derive this, become y prime, and this will be m e mx, and then derive again, it will be m squared e mx. Okay, and then we are going to input. So we are going to sub to the dE. Okay. Now our dE, let me write on the right side here so you can see the difference. So a m squared e mx plus b m, and then plus c e mx equal 0. So we try to factor e, and then we have a m squared plus bm plus c. Okay, now this one here, this am squared plus bm plus c, this will be auxiliary equation. And the one here, the e, it's always positive, so we can ignore that, right? It will not be 0, our 0, right? Because this is always positive. And since this is just a normal standard quadratic forms, so we can think in quadratic equation that we have done many years ago, right? So we can have based on the discriminant. Okay, so based on b squared minus 4ac, or we call this is the discriminant, we can have the discriminant is positive, which means that m1 and m2, this will be real and distinct. And then 2, if this discriminant is equal 0, the M1 and M2, this will be real and equal. So both have an equal. And if negative, M1 and M2, remember, if negative, which means that it is going to be an imaginary number, or it will be a complex. It will be conjugate complex. Okay, we are going to get into each one of them. Like what will happen if we have case 1, what will happen when we have case 2, what will happen when we have a case 3. So if you have a homogeneous linear equations, we can construct a way that we can have this auxiliary equations, and then looking for what kind of M we are going to have before we get the final solution. So it's actually, if you see what we have here, the construction here, it's not equal, but if we have, look here, so it's a y double prime, a m squared, okay, b y prime, b m, okay, and then c y, it's c. So we can directly see that we can get directly m, the auxiliary equation, from this part. Okay, so we can say that this will be am squared plus bm plus c directly. I'm not saying that this is like this equal to that, but we can trace out that it's actually going to be similar. Okay? It's going to be similar because remember, because of the e. When we derive e, it's appeared again and again, and then somehow we can factorize, and then we get the same structure, but changing the order with the m. Changing this order here, the dE, the differentials with the m. Okay. Okay. I think I can finish just for case 1 first, okay, and then the last 2 cases we are going to finish off later. Okay. So for case 1, case 1 is where the discriminant is positive. So we are going to have that y1 will be e m1x and y2 will be e m2x. These functions are linearly independent on all interval, or let me write that, and then we can write the general solutions as y c1e m1x plus c2e m2x. Okay, the other two, actually I can write case 2, but I think I will just keep case 1 first. The more complex one is the last one, the complex, because it's including the Euler formula, which I think I'm going to set or to find any additional informations. Maybe I'm looking from YouTube to give you some context on the complex. If I just give you the formula, you will feel like why is that happen? Okay. So I think this will be the end. Okay, this is the last time for the at least for auxiliary equations. Okay. So as long as it is homogeneous, we can use auxiliary equation, and then we can devise our proposed solution, which is the general solution. So it's actually like it's a part of the whole solution. If it is non-homogeneous, okay, remember, if it is non-homogeneous, we have YC and 1P, right? You can consider this auxiliary part is YC. So if this is not equal to 0, for example, okay, let me give you an illustration of what we are actually getting. Okay. If this is not 0, let's say you have another function here, maybe f of x. It will be non-homogeneous, right? But in non-homogeneous, if you remember, we are going to have a part from that non-homogeneous that is homogeneous. And then we have additional solution which we call the particular solutions. So the idea is still, we are going to use this a lot to give context to the homogeneous part. For non-homogeneous, there will be another method. So you see that, like, one sample problem maybe is going to take more than one method, maybe two, at least maybe two methods. And including the methods that you did in the first order. So probability is more complex than the first order. Okay, I think that's it for today. And please wait for my video. I think I also mentioned some parts on the first order differential equation, especially how to model or to simulate the system. I think I will just using some physics phenomenon, like maybe the difference in temperature or population, something